All right, today we're playing Cosmic Detective. We are opening up the case files on some of the universe's biggest puzzles, planets that seem to completely break the very rules of their own existence. These are the celestial bodies that, for all intents and purposes, just shouldn't be there.
See, for the longest time, astronomers had a pretty solid playbook for how planets are born. We had established theories, models that seemed to work, a general recipe for cooking up a solar system. It was all a pretty neat and tidy picture of how creation works.
But as it turns out, the universe loves a good plot twist. Lately, telescopes like the James Webb have started finding these worlds that are so bizarre, so completely unexpected, that they're forcing us to rethink everything we thought we knew. These aren't just little quirks. They're giant, flashing clues that our rulebook is missing some really critical pages.
Okay, so let's get into it. Before we can understand how the rules are being broken, we need to establish what those rules are supposed to be in the first place. What's the standard operating procedure for building a planet anyway?
Well, the main theory is something called core accretion, and it's actually a pretty straightforward idea. Just picture a brand new star, and it's surrounded by this big, spinning disk of gas and dust. Over time, little dust grains start sticking together, kind of like dust bunnies forming under your couch. And over millions of years, they crash into each other, forming bigger and bigger clumps until they grow into a solid core. Now here's the key. A planet can only be built from the material that's available in that disk. The size of the star determines the size of the disk, and that in turn puts a hard limit on how big its planets can get.
And that brings us right to our first cosmic cold case. Everybody, meet LHS 354b, a planet that is, by all accounts, impossibly massive for the tiny star it calls home. This thing is the heavyweight champion of how did that get there?
So, on the one hand, here's what we'd expect. A tiny M-dwarf star, only about 9% of our Sun's mass, should have a pretty small disk of planet-forming material. According to the rules, it should only be able to make small, rocky worlds, kind of like the famous TRAPPIST-1 system. But then you have the observed reality, a planet that is a whopping 13.2 times the mass of Earth. It's almost the size of Neptune, orbiting a star that's barely a star at all.
This chart really drives home just how absurd the mismatch is. It's showing the planet-to-star mass ratio. Just for context, our giant Jupiter is less than 0.1% of the Sun's mass, but the ratio for LHS 3154b is over 100 times greater than Earth's ratio to the Sun. The ingredients just don't add up. For this planet to even exist, the star's original disk would have needed about 10 times more dust than our models think is even possible.
And hey, don't just take my word for it. Suvrath Mahadevan, one of the astronomers who discovered it, put it pretty bluntly. This isn't just an odd find. It's something that flies in the face of our expectations. It really hammers home just how much more there is to learn. Okay, so if a planet that's too heavy is a puzzle, what about a planet that's orbiting the spinning corpse of a dead star? Let's open our second case file, PSR J2322-2650b. This is a planet that's not only surviving in one of the most hostile environments imaginable, but its very makeup, it just defies explanation.
I mean, this planet's profile is just bizarre. First off, it orbits a pulsar. That's a super dense, spinning neutron star that's blasting out beams of radiation like a cosmic lighthouse. The pulsar's insane gravity is literally stretching the planet into a lemon shape. And it gets worse. It's what they call a black widow system, which means the pulsar is actively eating its companion, stripping away its layers. But the weirdest part might be its atmosphere. Instead of the usual stuff, like hydrogen or methane, it's packed with carbon and helium. We're talking sooty clouds that deep inside might actually be getting compressed into real diamonds. And to give you a sense of just how extreme this whole situation is, look at this, 7.8 hours. That's not its day, that's its entire year. It whips around its dead star at a distance of just 1 million miles. That's about 100 times closer than we are to the Sun. The speed and the radiation it's enduring are almost impossible to imagine. The scientists who found this were just as baffled as we are. Peter Gao from the Carnegie Earth and Planets Laboratory pretty much summed up the team's reaction. This wasn't a discovery that fit neatly into any existing box. It was a genuine, what are we even looking at here moment. It defies every formation theory we have.
Okay, for our final case file, we've seen the impossibly heavy and the impossibly resilient. Now let's look at the impossibly light. Meet WASP 193b, a planet so huge and so lacking in substance that it's been nicknamed the Ghost.
And I am not being poetic here. That is the direct scientific comparison. The measured density of this planet is basically the same as that fluffy, sugary stuff you get at a carnival. It's an absolutely enormous world with almost nothing to it.
This table really puts it into perspective. Water has a density of 1. Jupiter is a bit denser, at 1.33. Even Saturn, the planet famous for being light enough to float in a giant bathtub, has a density of almost 0.7. Now look at WASP 193b, just 0.059. That's more than 10 times less dense than even Saturn. It's just wild.
So how is that possible? Well, this is the problem. The planet is enormous, about 50% bigger than Jupiter, but its mass is just a tiny fraction of Jupiter's, only about 14%. This means its atmosphere must be incredibly bloated, all puffed up by some kind of mechanism that our current models just can't explain, especially not over the billions of years it's been around. So what do we have? We have a heavyweight, a survivor, and a ghost. 3 planets that totally defy the standard model. So how do we solve these cases? Well, it looks like it's time to start rewriting the rulebook. Scientists are now digging for new clues and cooking up brand new theories to try and explain these cosmic oddballs. One of the first major clues comes from something called the Kepler dichotomy. Basically, when the Kepler telescope was hunting for planets, it found way more single-planet systems than our theories said it should. This is a huge hint that planetary systems might be much more chaotic, much more violent places than we thought, with planets crashing into each other or getting kicked out into deep space all the time. And that observation leads to this really fascinating new theory called breaking the chains. The idea is that planets might start out forming in a neat, stable, rhythmic chain like the TRAPPIST-1 system. But eventually, that chain becomes unstable. The planets start to wobble, their orbits cross, and then it's just total chaos. A series of violent smash-ups and mergers could leave behind a single unusually massive planet, which sounds like a pretty good explanation for our heavyweight LHS 3154b, doesn't it? It makes you wonder what our own solar system was like in its youth. And this is the most important takeaway here. These problem planets, these cosmic cold cases, they aren't failures of science. They are the exact opposite. Every single one is a breadcrumb, a vital clue that challenges our assumptions and pushes us toward a much deeper, more complete understanding of how the universe actually works. In the end, I think this sentiment from researcher Roger Romani says it all. The goal isn't to already have all the answers. The real thrill is in the chase. These impossible planets are a perfect reminder that the cosmos is under no obligation to follow our rules, and that the greatest discoveries often start with a single, completely baffled question: what the heck is this? Thanks for joining me on this one.